Hello students, I am Assistant Professor Dhanashri Sawan from Sambhajirao Kadam College Deur. Today we will discuss about our new syllabus NEP 2.0 of Shivaji University, BSc Part 1st, Semester 2nd, Department of Mathematics, Paper 3rd, Differential Equation. In Paper 3rd, first unit is Ordinary Differential Equations of a first order and first degree. So, what is ordinary differential equation? A ordinary differential equation involving derivative with respect to a single independent variable. Here is the example of ordinary differential equation. Dy by dx is equal to x plus cos x. Here y is dependent variable and x is independent variable. Next, partial differential equation. A differential equation involving partial derivatives with respect to more than one independent variable is called partial differential equation. Example is dou to u by dou x2 plus dou to u by dou y2 plus dou to u by dou z2. Next, order and degree of a differential equation. The order of a highest derivative involved in a differential equation is called the order of the differential equation. Example is dy by dx plus xy is equal to e raised to x. Here, order is 1, first order. Example second, dou 2y by dou x2 plus 4y is equal to cos x. Here order is second. Degree of a differential equation. The degree of a differential equation is the index of highest order derivative occurring in the equation which is free from radical signs and fractions. Here are the examples of degree and order. Exact differential equation. A differential expression m xy dx plus n xy dy is an exact differential in a region R of the xy plane if it corresponds to the differential of some functions f of xy defined in R. A first order differential equation of the form m of xy dx plus n of xy dy is equal to 0 is said to be an exact equation if the expression on the left hand side is exact differential. Here are methods to determine integrating factors. Next, linear differential equation. A differential equation is said to be linear when the dependent variable and its derivatives appear only in the first degree. A linear differential equation of the first order is of the form dy by dx plus py is equal to q, where p and q are functions of x or constants only. The solution of the equation dy by dx plus py is equal to 0, that is dy by y plus p dx is equal to 0, is y is equal to c into e raised to minus integration of p dx. That is y into e raised to integration of p dx is equal to c. This shows that e raised to integration of p dx is an integrating factor of equation first, as q is the function of x alone. Here solution of the linear equation. So we have dy by dx plus py is equal to q. Multiplying both sides by integrating factor e raised to integration of p dx, we get both side e raised to integration of p dx. Therefore, solving the equation, we get d by dx in bracket y into integration y into e raised to integration p dx is equal to q into e raised to integration p dx. Integrating both sides with respect to x, we get y into e raised to integration of p dx is equal to integration of q into e raised to integration of p dx plus c. Thus, the solution of the linear equation is y into integrating factor is equal to integration of q into integrating factor dx plus c, where integrating factor is e raised to integration of a p dx. Next, equations reducible to linear. Bernoulli's equation. An equation of the form dy by dx plus py is equal to q into y raised to n, where p and q are functions of x only, is called Bernoulli's equation. It can be made reducible to linear form by suitable substitution. Dividing the equation first by y raised to n, we get y raised to minus n dy by dx plus p into y raised to 1 minus n is equal to q. By putting u is equal to y raised to 1 minus n, therefore we get du by dx is equal to 1 minus n into y raised to minus n dy by dx. The equation 2 becomes 1 divided by 1 minus n du by dx plus pu is equal to q. That is du by dx plus 1 minus n into p into u is equal to 1 minus n into q, which is a linear equation in u and can be solved. Next, law of growth. One of the model for population growth that we considered was based on assumption that the population grows at a rate proportional to the size of the population. dp by dt is equal to kp. Is that a reasonable assumption? Suppose we have a population of a bacteria, for instance, with a size p is equal to 1000, and at a certain time it is growing at a rate p is equal to 300 bacteria per hour. Next, law of decay. Decay problems. The rate of decay of a certain radioactive substance is proportional to the amount of substance present. Let x be amount of substance present at any time t, then by law of decay dx by dt directly proportional to minus t. Therefore dx by dt is equal to minus kt. K is a constant. Integrating, we get log of x is equal to minus kt plus c. Therefore x is equal to e raised to minus kt plus c. That is x is equal to b into e raised to minus kt. B is a some constant. Next, Newton's law of cooling. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding, provided that this difference is not too large. This law also applies to warming. Next, orthogonal trajectories. When all the curves of one family of curve g, x, y, c1 is equal to 0 intersect orthogonally, all the curves of another family h, x, y, c2 is equal to 0, then the families are said to be orthogonal trajectory of each other. Thank you.